everyone, welcome back to the course Introduction to Infrastructure Asset Management. This course is offered under MOOCs, an initiative of Government of India. In this particular week, we have been discussing different considerations for infrastructure asset management. We saw that the goals are around three key items: performance, sustainability and resilience. In the earlier lectures, we have discussed about different sustainability considerations and different resilience considerations. In this particular lecture, I will discuss about performance considerations. This is the fourth lecture within this week where we will focus on performance considerations in infrastructure management. My name is Chirag Kothari. I am a faculty in the Department of Civil Engineering. Let us dive deeper into understanding what is performance. Performance in layman terms means how well a person, machine or a system does a piece of work. I am sure all of you have used terms like XYZ is performing well, A performs better than B and so on. In case of infrastructure, performance can be defined as how effectively an asset meet its defined service or operational standards throughout its life cycle. It is important to note that in this definition, the focus is on meeting defined service. So, we are just seeing how well an infrastructure meet its defined service or operational standards throughout its life cycle. Performance in the context of infrastructure is an encompassing term which includes several aspects. I will talk about them in detail in the next slide. It is important to note that performance goals can vary from one infrastructure to another. For a given asset, we might have different performance goal compared to another asset. Also, for the same asset type, it is possible that performance goals vary from one institution to another. So, let us see how do we understand performance of an infrastructure. An infrastructure's performance can be communicated with the help of following terms. 1. Reliability, 2nd. Maintainability, 3rd. Availability. All these three are important terms to understand performance. We will talk about them in detail. In addition to these three, there are other dimensions such as safety, comfort or convenience, as well as operational effectiveness. So, as I told, performance is an encompassing term. It includes different aspects such as reliability, maintainability, availability, safety, comfort and operational effectiveness. We will talk about them in detail. First, let us understand what are these three terms: reliability, maintainability and availability. Please note that this is a well researched area where there are several books around reliability engineering which discusses different aspects of failure, reliability and so on. In this lecture, I will just give you a brief idea of what these terms are and how they are used in the context of decision making. Reliability, maintainability and availability. First, let us look into these terms and their definitions and then we will try to compare them. Reliability is defined to be the probability that a component or system will perform a required function for a given period of time when used under stated operating conditions. Maintainability is defined to be the probability that a failed component or system will be restored or repaired to a specific condition within a period of time when maintenance is performed in accordance to the procedures. Availability is defined as the probability that a component or system is performing its required function at a given point of time when used under normal operating conditions. I request all of you to please pause the video and read these definitions again and look for minor changes in each of them. Reliability, as we talked about, is a probability that a system or a component will perform its function for a given period of time. It is important to note that in case of reliability, we are focusing on whether the system or infrastructure will provide services for a given period of time? Is it reliable enough to perform for a given period of time? On the other hand, in maintainability, the focus is on understanding how quickly can we restore or repair a failed component. The idea is probability that a failed component or system can be restored or repaired within a period of time. So, for example, we can define maintainability of an asset, can it be maintained within 2 days or maintainability of an asset within 5 days. There will be a probability associated with it. Maintainability refers to understanding whether the failed component can be recovered in a given time. Moving on, availability is slightly different from reliability. In case of availability, we are looking into whether the system or component is expected to perform at a given point of time. Please note, the focus is on a given point of time. In case of reliability, we were seeing whether the facility will function for a given period of time. Here, we are only focusing on at a given time whether the system is functional or not functional. I hope these three definitions of reliability, maintainability and availability are clear. Please note that these terms are defined under normal stated operating conditions. Please look into that. In each definition, I have written under stated operating conditions. This is important to note that these terms in this context are defined for normal conditions. These are not defined for extreme conditions. We are not getting into the discussion on resilience here. The focus is on asset performing reliably under normal operating conditions. There are detailed courses, books and references available around understanding reliability engineering or understanding reliability in engineering. We will put some of those references at the end of this lecture. For our discussion, we need to understand that any reliability function R is given as probability of the asset performing over a given period. So, in this case, we say reliability is the probability of capital time T, which is the time to failure, being greater than or equal to the time period. So, if I want to understand what is the probability that my asset will perform at least for 5 days, then I can write what is the probability that the time to failure, which is capital T, will be greater than or equals to 5. This is known as reliability. Here we can see that R of 0 will be 1, because you can say that the reliability that an asset will perform for 0 time is definitely 1. On the other hand, R of infinity, that is the possibility or the probability that an asset will perform for infinite duration, is obviously 0. So, I hope these two extreme cases are clear. In this context, once we have reliability defined, we can calculate what is the failure distribution function. Given R of t, can you think about how can a failure distribution function be defined? Please think about it before moving on with the video. I hope all of you have written failure distribution function or cumulative failure distribution function as something like 1 minus the reliability, which is equals to the probability of small time t less than equals to capital T. The idea is simple, that if reliability is equals to say 60%, which means there is a 60% chance that the asset will perform for a given period time t, which is small t here, we can say that the failure chance is obviously 1 minus the reliability, and we can calculate that. This is a cumulative distribution function for failure, written as capital F of t. In this context, it is important to know that reliability is different from quality. We often use these two terms to talk about an infrastructure's performance. We want it to be of good quality as well as reliable. The question is, what is the difference between these two terms? Quality is defined as how well the product satisfies users' requirement. On the other hand, reliability is defined as maintaining performance and functionality over time. So, the notion here is, what is the quality of a product over time? Reliability is a measure of dependability. In the case of quality, we are just focused on how well the product satisfies users' requirement. But we know that the performance or quality of an infrastructure deteriorates with time. So, reliability is defined as how well an infrastructure can maintain its performance and functionality over time, or how well it can maintain its quality over time. So, I hope the difference between these two terms, quality and reliability, is clear. Now, with this idea, let us go back to our definition of reliability or failure. We have already seen that cumulative distribution function for failure, capital F of t, is equals to 1 minus the reliability. Once I know this, I can also determine small f of t, which is the function for failure, which will be a differentiation of this, which is given as minus dr of t divided by dt. These terms are interrelated, f of t, capital F of t, r of t, and so on. There is another term which is commonly used in this context, is mean time between failures, MTBF. This measures the average operating time between asset breakdowns. The idea is that we are recording the time between two failures. What is the average operating time between two breakdowns? This serves as a fundamental indicator of an asset's reliability. Obviously, if the mean time between failures is high, it means the asset is reliable. A longer MTBF indicates better reliability and fewer maintenance interventions required. With age, it is found that MTBF typically decreases, signaling the need for increased maintenance. As discussed, this is just a brief introduction about reliability. If you want to get into details of it, there will be some references at the end which can be used. Now, let us discuss quickly what are the requirements for doing reliability analysis. First important consideration here is, we need to ensure that we have an unambiguous description of failure. We need to really define what is failure. For an asset, when do we say something has failed? Also, we need to define how failure can be observed. We should have an observable description of failure. For example, if there is a failure occurring within a structure, but you cannot see it, then it is difficult to understand at what time failure has occurred. Thus, we need to define failure as something which is observable and unambiguous. Also, the system should be performing under normal performance or under normal stated conditions. Applications, as I discussed, includes small f of t, capital F of t, r of t. We can define all these functions. We can understand what is the mean time to failure. We can understand what is the failure rate. These parameters can be used to understand when predictive maintenance should be carried out. After discussing about reliability, I want to take a minute to discuss about maintainability. As we saw, maintainability is defined as the probability that a failed system or component will be restored or repaired within a given period of time. Similar to reliability, we can also write a mathematical function for maintainability. A key term which is used in this context is MTTR, which is the mean time to repair, quantifies the time required to restore failed assets to its operational status. This is the average time which was required to bring a failed asset back to its normal operating conditions. Lower MTTR indicates how efficient maintenance processes are and how quickly we can restore the asset. This matrix reflects both the possibility of an asset to be maintained, that is maintainability of asset, as well as it talks about the effectiveness of the maintenance team. I hope this idea is clear that mean time to repair will be impacted by two things: whether the asset can be maintained, which is maintainability of the assets, and the effectiveness of the maintenance team, which is responding to issues. Having discussed reliability and maintainability, I will take another minute to talk about what is availability. As discussed, this is the probability that a component or system is performing its required function at a given point in time when used under stated operating conditions. Again, we can have a mathematical function which can be used to derive this, but it is out of scope for this particular course. However, please note that there are two dimensions to availability. One is assets availability and the second is systems availability. In case of asset, we are focusing on an individual asset and we are trying to understand what is the percentage of time an asset is operational or it is available to perform its required function. On the other hand, system is a more broader term. Instead of focusing on a single asset, we are looking into a group of assets or an infrastructure system, and we are trying to understand what is the percentage of time under which an infrastructure system is operational, or what is the probability that an infrastructure system is performing at a given point of time. I hope the difference between these two is clear. A system might have multiple assets. Moreover, it might have redundant assets. For example, if there is an asset where you feel the reliability of this asset is low, then in order to ensure that the system is performing, you might want to have multiple assets being part of that system. So, you want to have multiple redundant assets, so that as long as one of those assets is performing, the system can perform. Thus, in case of an infrastructure system, the focus is more on systems availability. Is the entire infrastructure system available or not? Instead of focusing on one component or one asset, we are more concerned about the overall system. That was a very brief introduction to these three terms around reliability, maintainability and availability. These are the three performance dimensions which are often used in the context of infrastructure. In addition to these three, there can be other performance dimensions like safety, which talks about the number of accidents or reduction in accidents. Operational effectiveness, which talks about what are the productivity gains from an asset, or alternatively what is an asset's utilization rate, how well an asset is being utilized for the overall gains. These can be different performance dimensions. You might have a performance parameter where you want to keep an asset's utilization rate to be high. Moreover, we can have aspects of comfort and convenience. In case of infrastructure, this is very important, where we say an asset is performing as long as it is providing convenience to the users. If there are enhanced user benefits, then we can say the asset is performing. In case of infrastructure assets, performance is key. How well an infrastructure asset is meeting the demands can be communicated with the help of performance. The question of why we are concerned about performance is straightforward. We want an infrastructure asset to perform. Governments worldwide prioritize infrastructure performance because it is a fundamental pillar for national stability, economic prosperity and social welfare. Infrastructure assets performing helps in business success, operational continuity and competitive positioning of a government. Moreover, infrastructure failures That is, if an infrastructure is not performing as required, these failures are found to cascade through various aspects of economy and businesses, and they create exponential cost and consequences which are far beyond the immediate technical issues. Thus, the focus is always on ensuring that the overall downtime is lowered. Infrastructure system being down is directly impacting the economic growth and community welfare. An infrastructure is expected to perform because it will eventually impact the overall economic growth, public services, public safety, national security, social welfare, disaster resilience, fiscal response, public trust and sustainability goals. Please note the two terms around resilience and sustainability are included here to improve sustainability as well as to improve resilience efforts. We want an infrastructure to perform well. To achieve resilience and sustainability goals, it is prudent that an infrastructure even performs well. Performance has been a primary criteria which is used by a lot of decision makers. The latest development in the context of India, which is the National Infrastructure Pipeline, also reflects the government's focus on recognizing performance management as an essential for sustainable development. So, performance is a key parameter which is taken care during decision making. Now, let us see how performance goal translate in the context of infrastructure asset management. Similar to sustainability and resilience, I will take a small case example of highways. Performance in the context of infrastructure asset maintenance refers to a comprehensive measure of how effectively and efficiently assets are maintained to ensure they deliver their intended functions. This includes setting up measurable performance targets or service levels, for example, performance target around safety, condition, capacity and so on. Then monitoring and evaluating assets against these targets using suitable performance indicators. Then trying to predict potential failures or potential issues in services, and then making informed decisions on interventions such as maintenance, repair or replacement to sustain or improve the asset's performance over time while balancing cost, risk and service quality. With this background, let us discuss how different performance parameters can be defined for highway assets. An highway engineer who is responsible to improve the performance of highway assets is likely to focus on different aspects of reliability and availability. Here the focus is on how reliable an asset is, that is, whether the asset is available to use. Moreover, how reliable is the trip time. You want to ensure that the time it takes to travel from point A to point B should be reliable. The deviation in the trip time should be low. Also, it could include ensuring availability and access of transportation systems. A transportation system should be available when it is required. In the context of safety, an highway engineer will focus on injuries or fatalities per unit of transportation. The goal will be to reduce the number of injuries and achieve zero accidents. In addition to accidents, the focus can be on user awareness. There can be a performance criteria which tries to understand the user awareness around safety. Then the aspect of maintainability will focus on what is the time required to repair a section of road, what is the availability of machines and manpower to ensure that the maintenance can be carried out in a decent amount of time. In reference to operational effectiveness, the focus can be on the average road user cost. You want to reduce the average road user cost. Also, you want to reduce the traffic delay due to work zone. Also, you want to increase the overall level of satisfaction. Also, you want to improve the effectiveness of the maintenance which is carried out. So, these are some of the examples of how performance can be defined in the context of highways. I am sure some of you might be thinking that these performance parameters which are listed here, some of them are also overlapping with some of the other goals in sustainability, where we discussed about economic goals as well as equity goals. This is how performance of an highway network can be measured or assessed. I am sure some of you might be wondering that some of the parameters discussed here are overlapping with what parameters we had discussed for sustainability, especially within economics and equity goals. You are right, some of these parameters are often interlinked with each other. On improving one, you often improve another one. However, there are possibilities where improvement in one of the indicators can actually conflict with another indicator. So, these objectives are interconnected. In some cases, they are directly proportional, but in other cases, they might be indirectly proportional. In addition to these performance indicators, there are other indicators used in the context of infrastructure asset management. Some decision makers like to use ratios between planned versus unplanned downtime. The idea is an asset will always have some downtime. You want to maximize the overall planned downtime and minimize the unplanned downtime. You want to be in a situation where you are already aware that an infrastructure asset will need to be repaired, and you are doing a more proactive maintenance rather than a reactive maintenance. Same thing can be communicated using percentage of planned maintenance versus total maintenance. You want to ensure that the percentage of planned maintenance is high in comparison to total maintenance. This effectively means that unplanned maintenance or corrective maintenance was lower. Another parameter here is preventive maintenance compliance. What is the percentage of scheduled maintenance tasks completed on time as per the schedule? The idea here is that there is a maintenance schedule, but are you really maintaining as per the schedule? Are you sticking to what you had planned? This is another performance criteria where percentage of scheduled maintenance tasks completed on time as per schedule can be a parameter. Then the overall cost for producing one unit is again a performance criteria. You want to ensure that the overall life cycle cost is reduced so that the cost of producing one unit is reduced. Then another criteria which can be used is maintenance cost as a percentage of assets replacement value. This is another indicator which gives us an idea of how much money has been spent on maintenance and what is the proportion of that money with respect to an asset's replacement value. So, these are some of the other performance indicators which are used by decision makers. As I told earlier, performance can be defined differently for different assets. Also, for the same asset, a decision maker or an organization might define performance separately. With that, I end my discussion on performance considerations for infrastructure management. In this particular lecture, we saw that performance goals are key to infrastructure asset management decision making. Performance has been a key decision factor when taking important decisions. In the recent times, sustainability and resilience have been added to the overall decision making framework, but performance has been there for a long time. We have seen in this particular week that infrastructure decision making needs to account for performance, sustainability and resilience goals while developing asset management plans. We have also seen that this is a challenging task because it involves several interconnected objectives. As I just mentioned, some of the objectives which we have are interconnected. If you improve performance, you might improve the economic sustainability. Alternatively, if you improve performance, you might eventually improve resilience. Alternatively, if you focus on performance and use a material which is highly durable, that might come at a higher economic and environmental cost. So, you might get higher performance, more durability, but that might be at the cost of higher money spent as well as higher damage to the environment. So, as a decision maker, this becomes tricky. These objectives are interconnected, but they might be supporting or conflicting each other. Thus, from a decision maker's point of view, they need to rely on some multi-criteria analysis methods or multi-criteria optimization to take such M&R decisions. Ideally, we would have liked that there are a lot of data sets available so that these parameters can be understood in detail using empirical data. However, in the absence of reliable data, multi-criteria analysis approach has to rely on relevant experts to provide appropriate criteria weights. You want to understand how important a given criteria is in compared to other criteria. With that, I want to end our discussion for this particular week, where we focused on performance, sustainability and resilience. We saw what are the different considerations within performance, within sustainability and within resilience. We also talked about the fact that these are the goals of infrastructure asset management. You want to have an infrastructure management system which is performance driven, sustainability driven and resilience driven. In the context of the discussion we have been having in the last 3-4 weeks, we have seen that this entire process of infrastructure asset management is centered around policies and goals. In this week, we saw how some of these policies and goals are determined and how performance, sustainability and resilience are the key dimensions to think about relevant goals. Now, if we try to retrace this flowchart again, what we are saying is we need to collect relevant data around performance, sustainability and resilience. Then we need to conduct performance modeling. We might actually need to conduct sustainability modeling as well as resilience modeling. Then we need to determine what are the different alternatives, what are the different M&R options available, and we need to see what is the cost associated with each of these maintenance or rehabilitation technique. We also need to see what is the overall impact of these maintenance and rehabilitation techniques on the performance, sustainability and resilience of an infrastructure system. For the decision making, we have already discussed that there are different ways to take this decision. Here, the whole idea is we are trying to understand which infrastructure asset needs maintenance, what type of maintenance it needs and when does it need a maintenance. We have seen that this process is known as selecting candidate projects, where we discussed different techniques like subjective experience, decision metrics, decision tree and optimization. Given that a holistic infrastructure asset management has to rely on multiple criteria of performance, sustainability and resilience, it might be difficult to take this decision subjectively. Thus, the decision makers are encouraged to use decision metrics or decision trees. However, as we have seen, decision metrics and decision trees also do not account for the amount of money which is available for our decision making. However, we have seen that decision trees and decision metrics don't account for the amount of money which is available for maintenance of our assets. Moreover, we just now saw that a lot of parameters we have in our mind might be conflicting with each other, or some of them might be supporting with each other. To make a decision matrix based on these considerations might be difficult, especially when you are creating a multi-year plan. That is where optimization comes handy. We have already seen what is optimization. In this context, what we are saying is, for our decision, we will have multiple objectives. We can have things like minimize environmental damage, maximize performance, where obviously performance is defined using several indicators. You might want to maximize some of them or minimize some of them. We can also have things like maximize fairness in the network, which is a parameter for equity, and so on. So, the whole idea here is that this budget programming using optimization is a multi-objective problem. There are several objectives which can be used to define performance, sustainability, and resilience. Moreover, there can be multiple constraints. For example, budget is a major constraint, but there can be other constraints. You do not want an asset to be maintained more than once in 2 years, or you do not want the road user cost to go really high, or you do not want the entire amount of money being spent only on a small section of infrastructure, and so on. So, there can be multiple constraints. Then the focus is on having a multi-year plan. You want to do a more holistic planning where you look into a network of assets for the next 5 years, 10 years, or 20 years. You do not want to take decision based on the current condition. You want to make a more informed decision which focuses on a multi-year plan. This is where, as we discussed in optimization, that we want to use a comprehensive optimization framework which focuses on which infrastructure to maintain, when to maintain it, and how to maintain it, or what actually to do to maintain that particular asset. And we need to take this decision while ensuring that the candidate projects we have meet our budget requirements. Budget requirements or budget constraints can be determined using several aspects. The economics around this can be communicated using different terms like the cost benefit analysis, the payback period, or the overall life cycle cost. We might use terms like net present value or internal rate of return to see what is the benefit of doing one maintenance over another, or what is the benefit of doing maintenance over not doing any maintenance. So, thus in addition to all the technical parameters, economics also plays a critical role in the decision making. With that, we end our discussion of these 4 weeks where we have discussed a generic thought process which can be adopted on any infrastructure system based on the decision maker's requirement. Different aspects of budget planning, budget programming, AHP for multi-criteria decision making, optimization for decision making, economic principles like net present value and rate of return, payback period, economic decision making, so on have been discussed. Also, different considerations of performance, sustainability and resilience have been discussed. How these goals translate to different indicators or objectives has been discussed. The last 2 steps of this particular flow chart are implementation and monitoring. We have discussed in detail till decision making, and we have seen how goals, budget and policies impact our decisions. However, we need to acknowledge that any decision we take is based on several assumptions. It is based on the data which is available to us, it is based on the models which we have created for performance and so on. Thus, it is important to implement these decisions but at the same time monitor them. For example, when we are creating a 20-year plan, you are kind of deciding all the maintenance activities which are required for the next 20 years. But this is not a one-time exercise. We need to continuously monitor our assets. We need to see what is the current performance. Has the performance deteriorated at the same rate of what we had expected, or has it changed? So, there is a need to do continuous monitoring, which actually serves as a feedback. We might need to redefine our performance model. We might need to change some of the parameters we have in our decision making framework, and so on. Thus, it is important that implementation as well as monitoring go on hand in hand, and we continue to update our maintenance and rehabilitation plans again and again every time we get new data sets. Here are some of the references and suggested readings which can be used. Some of these books get into the details of how to conduct reliability analysis for engineering systems. Thank you. Thanks for listening.